Hello friends, welcome back. So in the previous video, we learned about matrices. In this video, we'll be learning about something which is very intrinsic to matrix, known as a determinant. So what exactly is a determinant? The determinant is a real number associated with a square matrix. So first of all, we had learned about a lot of different types of matrices, right? Here we are considering only square matrices. So determinant is a real number associated only with the square matrix. With any other matrix of different order, we cannot have a determinant. Right. So how exactly do we find out the determinant of the square matrix? Well, so we have a few rules here. So let us get down to those rules. First of all, when there is a square matrix of order 1, right? So let the element be A. Now the determinant is written like this, right? So instead of the square brackets, we have two vertical lines, and for this the determinant is the number itself, A. But now, once we go to the second order, it gets a bit complicated. And for this, well, we write it like this. This is the determinant, this was the matrix, right? This is the matrix, this is the determinant. And this is given by A11, A22 minus A12, A21. Right? This 21. Okay, so these two multiply, and then these two multiply, and the second product is subtracted from the first. Right? So even for the second, for a square matrix of order 2, it's not that difficult. But once we go to the third order, and so before that we define two key concepts known as minor and cofactor. So what exactly is a minor? Okay. Now, for any element in a square matrix, once you delete the same row and the column as the element, the determinant you obtain, right, of the remaining elements, that is known as the minor of that element. Right? So if I have Aij, its minor is denoted by Mij. So let us first take a 3 by 3 matrix and explain this. A11, 12, 13, 21, 22, 23, 31, 32, 33. Right? So this is my square matrix of order 3. Now here, suppose I take the element A11, right? So this is my the same column and the same row, right? So whatever is remaining now, A22, A23, A32, A33, which is a square matrix of order 2. So obviously, Mij will always be of order n minus 1, right? If n is the order of the square matrix, the minor of any element will be of order n minus 1. Now, the determinant of this is known as the minor, right? So, this is how you find out, and now we know that the minor is nothing but A22, A33 minus A32 into A23, right? Which comes from just the previous page. Now, minor in itself is not that important. What is more important is cofactor, right? So, for the same element Aij, the cofactor is written as Cij, which is minus 1 power I plus j into Mij. Okay. Now, how do you exactly find out? So, what exactly is the importance of Cij here? This is the. So there are a couple of properties here. The first one is, suppose I log any of these. Now, every element or even cofactor for that matter has two different indices, right? I and j, depicting the rows and the columns. Now, if I log any of these indices such that that index is same for both the element and the cofactor, right? I multiply the corresponding cofactor and elements of any row or column. Right? So what I do is, just for illustration, I will take that logged index as the row, and that is as row 1. So I have A1, C1, right? So that is logged, and then I permute it over the other index. Sorry. This is nothing but a determinant which is denoted by the Greek symbol delta here, right? So suppose I take the first row here, this one. So A11, its corresponding cofactor C11, I multiply it. That similarly multiply A12 and C12, similarly A13 and C13, and I add all of them. What I get is nothing but a determinant delta. At the same time, if I take the corresponding cofactors of any other row, right? So I do something like this: A11, C21, right? This is the first element of the second row. Similarly, A12, C22, A13, C13. This is always 0, right? So whichever index I log, suppose I log the row right here, and if they are equal, then I'll always have delta. If I log say this different rows here, and if they are, and since they are not equal, I'll always have 0, right? So this is the second case. Right. Now let us move to some of the properties of determinants. How to evaluate them? There are a lot of properties which help us in simplifying the determinants. So first of all, let us look at the determinant of a 3 cross 3 matrix. So I have A11, A12, A13. Right? This is given by, so I expand it using my first row here. You can expand it using any row or column, right? So there are actually 6 different ways of expansion, all of which are perfectly same. Right. So A11 into the cofactor of now its cofactor. So its cofactor is nothing but A22, A33 minus A23, A32, right? And then minus A12. Why do I write minus here? Minus is because the cofactor will have that extra part minus 1 for I plus j, right? So 1 plus 2 is 3, and hence I get a minus n here. Right? And the final term here, A13, again plus here because 1 plus 3 is 4, minus 1 plus 4 is 1. So, right. This is my determinant of order 3 with the elements A11, A12, A13 till A33. Right. So let us now look at the properties. Now I just said that the determinant of any matrix, the determinant of any square matrix can be evaluated using any row or any column, right? So the first property is, if you interchange the rows to columns, there is no change in the determinant. Right? Or in other words, what this means is the transpose of a matrix will have the same determinant as the matrix itself, right? Suppose A is a matrix and its transpose is given by A superscript T, so its determinant is the same thing as the determinant of A. Right. The second one is, if I interchange any 2 rows or 2 columns, right? So suppose I take the first row, this one, and I interchange it with the second row. Okay, so that makes my new matrix as, or the new determinant as A21, A22, A23 as in the first row, and then A11, A12, A13 in the second row. Right. So what this does is, this negates the determinant. Okay, so my new determinant is negative of our original determinant. Now I'll be discussing all of these properties with rows, right? But these are perfectly same even for columns. Right? So delta dash here is the new determinant and delta is the original determinant. So it's minus delta. The third property is if two rows have the same elements, then delta is equal to 0. Right? The determinant of the determinant is 0. Now here the same elements mean the same corresponding elements. Okay, so the same elements will not be in any order. They have to be in the exactly same order. Now, if any element in a row or a column, if all the elements in a row or column are 0, even then the determinant is 0. Right? Because while expanding, we will take that determinant and expand using, we will take that row and expand it using that row. And as you can see, that the determinant is nothing but that element multiplied with its cofactor. So, since the element itself is 0, we'll get the determinant also as 0. Okay. Now, this property is a very nice one. The next one. If you remember, in scalar multiplication, what we observed was there was a matrix A, and I multiply it with a scalar K. What happens is every single element of the matrix is actually multiplied with K, right? Whereas this is not the case with a determinant. What happens is if I take the determinant of a square matrix and suppose I multiply any given row or a column with the square matrix, the determinant of the new matrix is K times or the scalar times the original determinant, right? Right. So if you actually analyze this, what happens in the case of a 3 cross 3 matrix? Suppose I had a 3 cross 3 matrix by the name 3 by 3 square matrix A, and I take and I multiply it with scalar K. What I obtain is K times A, right? But now I take its determinant A, right? And I do the same. I consider the determinant of Ka. Now what happens is since Ka is multiplied by Ka multiplies each element with that scalar K, and now from this property K times any row gives me a product or a factor of K with the original determinant. Hence, and since this was a 3 by 3 matrix, we will get this as K cube into determinant A. Right? So it's no more K into determinant A, it's K cube into determinant A. Okay, so this is a big change here. Now this is 3 here only because we consider it a square matrix of order 3. In general, this will be K power n. Okay. Now the next property is this one. Now using the fourth and the using the third and the fifth, we obtain a very nice property which says that if two rows have elements in the same ratio, right? Even then the determinant has to be 0. Columns. right? It's very easy to see how. Suppose my first row is A1, A12, A13, and the next row is say since they are in some ratio. Let us say the second row, that is A21, A22, and A23. I write that as K times A11, K times A12, K times A13. Now what I can do is I can take this K from the second row common, right? And once I take that common, I reduce to a matrix which has, or determinant which has the first and second row exactly same, right? And from the third property, we see that if any two rows have same elements, the determinant is 0, right? So that is how we use these two properties to derive another property such that the determinant is again 0. Now this property can be further used to make a very important property which is generally used in solving determinants. So this says, okay, so before that we need to describe another property, that is right. So if each element in a row or column is written as the sum of two or more terms, then determinant is equal to sum of two or more determinants, right? So suppose I take the second row and I can express all the terms as say a plus b, c plus d, and e plus f respectively, right? The first element in the second row is a plus b, the second is c plus d, the third is e plus f. So what I can do is I can write two different determinants such that the first determinant will have a, c, and e, and the second will have b, d, and f, right? You can interchange them, right? You can write instead of a, c, and e, you can probably take a, d, and e, right? Instead of c, you can take d. That's what I changed in the second way, right? So the critical thing is you can just separate them and write them as two different determinants, obviously such that the first and third rows are the same as the original determinant, right? So this is what you can do, and so the determinant is just the sum of these two new determinants now. This can be done more and more number of times as well. So combining this, we get this condition. Right. So to each element of a row or column, we add equimultiples of one or more parallel lines. The determinant remains unaltered. Now, parallel lines here means, say, if I am considering a row, so I can only take the other rows. I cannot take columns, right? So, if to each element of a row, we add equimultiples of one or more parallel lines, the determinant remains unaltered. I'll just show this one. What I do is, I first consider A1, A2, A3, B1, B2, B3, C1, C2, C3, right? Now what I do is, I take the second row and the second column and the third column, and I consider two new scalars L and M I multiply L with all the corresponding elements of second column and M with the elements of third column, and I add them to R. The first column. This is actually written as C1 undergoing the change C1 plus L C2 plus M C3. So we'll learn more about these in the questions. I'm just telling the notation here. So what happens is A1. This is my new first column. A1 plus LB1 plus MC1. Similarly, A2 plus LB2 plus MC2. A3 plus LB3 plus MC3. The other columns are exactly same. They have no change. Now this determinant is exactly the same as the original determinant. You can easily see how. First of all, using the seventh property here, we can write. We can write this determinant as a sum of three different determinants, right? So I have the first one as this one, the original one. The second will be LB1, LB2, LB3, and then the second and third columns. And similarly, the third one will have MC1, MC2, and MC3 in the first column. And then you can using the sixth property here, we see that LB1, LB2, and LB3 have the same ratio in the second column, right? L. So we can write the determinant as 0, and similarly the third determinant, and hence you see that the determinant is not changed. Right? So this one is of a lot of importance in solving determinants. Actually simplifying it. Now for those who have already learned calculus, okay, before that let's learn product of determinants. Right. So suppose I have two determinants A1, A2, A3, B1, B2, B3, C1, C2, C3, and I have alpha 1, alpha 2, alpha 3. Right, so these are two determinants. How do I exactly multiply this determinant as one determinant? So what I do is, there are four different rules we can follow here. The first and the most usually used method is row by column method. The one which we use for matrix multiplication. In matrix multiplication, you have it fixed, right? You have to multiply row by column. If you have seen the previous video, you know that matrix multiplication is always done by row by column method, right? So this row by this column, and then again this row by this column, and so on, right? I'll just remove these lines now. But with determinants, since determinants remain unaltered for interchange of rows and columns, that actually helps us a lot, because we now have the freedom to do it row by row, right? So initially, what the most common one was row column, but instead of that we can now do row or row column. Row means row and row, right? You can multiply the corresponding elements. You can also do column, row, and finally column. Right. So I'll just write a few terms here. So here, doing it by column method, we see that the first element here will be now A1 alpha 1 plus A2 alpha 2 plus A3 alpha 3. Similarly, the next one will be A1 beta 1, A2 beta 2, A3 beta 3, and so on, right? This is actually a pretty huge one. 9 terms here, and then you have to do this multiplication and addition every single time, and then you can write the whole thing. So this is how you can obtain the product of two determinants. Right? If there are more than two determinants and you are supposed to multiply them, take any two and then multiply them first, and then take a third one, then the fourth one, right? So multiply two at a time and then proceed further. So now, for those who have learned calculus, so you know what differentiation and integration is. So how exactly can we differentiate determinants? Right? So this is my delta of x. Right? Obviously, differentiation can be done only of a value which is changing, right? Otherwise, if you take a constant value differentiation, the derivative of that will be zero. Right? There is no change. Differentiation is nothing but change in that value. So if you consider only till now we are considering only constant numbers, right? So instead of constant numbers, if we give them some kind of change, right? If we make them a function of some other independent value, then we can observe some kind of derivative there, right? Some kind of change. So suppose I just consider here a 2 by 2 matrix to understand to make you understand this. So suppose this is A11x, A12x, A21x, A22x, right? So derivative of this determinant, which is a function of x here, what we do is you have the first of all you have the liberty to choose either the row or the column, right? So if you take the row, I'll take the row here. Differentiate all the elements of the row, keeping the others fixed. So I differentiate the first row here and add it to the determinant obtained by differentiating the second row. A21 dash x. This dash obviously, these prime here, the symbol obviously represents the derivative of a11 of x with respect to x. Right? So this is the general rule for differentiating a determinant. So you keep differentiating one row or one column at a time. Right? So you either fix it for column or row, and once you determine that, you keep differentiating one row at a time, and then you similarly differentiate all the rows and add these determinants. So that is how you find out the differentiation of determinants. Similarly, we can integrate them. Right. So here we have, suppose I have a 2 cross 2 matrix. So the first row is f of x and g of x. So right, I have two functions of x here. Whereas the next are just two constants a and b. Now if I integrate delta of x, what I do is I just integrate the first. I just integrate those individual elements f of x and g of x, right, whereas keeping the others constant. So this is how I obtain the integral of my determinant. Right. Now, once we are done with this, we'll move to a few concepts which are not taught in matrices, which rely a lot on the knowledge of or the understanding of determinants. So the first of this is adjoint. So adjoint of a matrix. Now an adjoint of a matrix is nothing but the transpose of matrix of cofactors, or the transpose of cofactor matrix. Right? So we now know what cofactors are. So suppose I have this 2 by 2 matrix, and the cofactor matrix is now nothing but C, capital C, right? Capital C11, C12, C21, C22. Now what I do is I transpose this. So I have C11, C12, C21, C22. Right? So this is my adjoint matrix, the adjoint of my original matrix. So what is this? This is nothing but transpose of the matrix of cofactors of the elements of A. So A is written as Aij. The uppercase C will be nothing but the adjoint matrix, which is nothing but Cij in its compact form. It's also written as small lowercase adj into A. Adj A. Right? So this is nothing but adjoint A. Now, very important property here: A into adjoint A, right? Because adjoint A is a matrix and A is also a matrix, and since both of them are of the same order, actually both of them have to be square matrices here. And adjoint can be defined only for square matrices. So A into adjoint A into A is equal to A into I. Right? So A here, this is nothing but our determinant. Okay. So this is a very important theorem actually. First of all, A and adjoint A, and both of them, so they are commutable under multiplication. So A into adjoint A is the same thing as adjoint A into A, which is equal to determinant A into I. Right. Now using this, what we do is we define something known as inverse of a matrix. Now, suppose we have a square matrix A, and we somehow find another matrix B such that A into B actually gives us I. Right? Now, in this, any such matrix B which when multiplied with A gives us I is known as I is the identity matrix. So this matrix B is nothing but the inverse of A. Okay. Now, first of all, AB they are also commutable under multiplication. So I can also write that as B into A. Okay. So B is actually written as A inverse. So A power minus 1. So this denotes the inverse of A. Now, if you look at the previous theorem, I had A into adjoint A is equal to A into I, determinant A into I. Now, you all know that determinant is just a real number, right? So, division of matrices is not permitted, but division by real number is always allowed. So, what I do is, I divide the whole thing by the determinant of A, right? And I write it in the adjoint A. Okay. Now, if you compare this form with this one, what you see that this part here, 1 by determinant A into adjoint A, this is nothing but the determinant, right? So this gives us a very important formula to determine the inverse of a matrix, which is given by. So this is the formula to determine the inverse of a matrix. Now, once we have done this, let us write a few important properties of adjoint and determinant. First of all, inverse of a matrix is unique. Now, there is a very important property I missed here. The inverse of a matrix is not defined for all matrices, right? As you can see from this formula, A inverse is 1 by determinant A into adjoint A. Now, an adjoint matrix can be easily found out, but what if the real number determinant A turns out to be 0, right? So, for all the cases where determinant of A is 0, the inverse does not exist, right? If you remember, the matrices where the determinant is 0, they are known as singular matrix, which is covered in the previous one. I just given the definition there. So, matrix whose determinant is 0 is known as singular matrix, and all these singular matrices will not have their inverse. So, this is defined only for non-singular matrices. right? So if the inverse exists, that inverse is unique. Similarly, now the reversal law works here as well, right? As in the case of transpose. So if I multiply A and B and I take its inverse, it's the same thing as B inverse A inverse. And A inverse then transpose, the same thing as A transpose and then inverse. Even the adjoints follow the reversal law, and hence adjoint AB is the same thing as adjoint B into adjoint A. Right? If you take the transpose of A and take its adjoint, is the same thing as taking the adjoint and then transposing it. Right. Now, once we are done with all this, let us now look at probably the most important reason why the topic matrices and determinants was started. Right. So, matrices and determinants were started to solve a system of equations. Right. Now, so we have two different ways to solve a system of equations. We will consider both of them. First of all, let us write down our system of equations here. Right. So suppose I have n unknowns. These are the unknowns here. Oh, sorry, this is not x1, just x1. Right, so you get it how they are written, and this way in A and N. So I'm sorry. Right. So this is my system of equations here. This denotes that there are n different conditions I have. Right. These are all conditions. These are all those n different conditions in n, and I have n different unknowns. So what I can do is I take these coefficients a11, a12, a1n, and all the way till ann. Now, as you can see, they form a square matrix, right? So that is my capital A. A1 was A. Right. So this is my my coefficient matrix A. I then consider my unknown matrix X. Now this is just a column matrix, right? This is just x1, x2 till xn. If you actually look at these two, they actually multiply to give you this the left hand side of all these equations, right? The matrix multiplication actually gives the left hand side of these equations, and then I consider capital D, right? The right hand side part, which is also a column matrix. Now, hence, writing these as matrices gives me this beautiful condition Ax is equal to D. Now here, what I do is I multiply both sides with A inverse. And so, the inverse of a matrix multiplied with, so I multiply the right hand side also from the left side. So I have A inverse on the left side here, right? Now, A inverse into A or A into A inverse is identity matrix, right? And that identity matrix multiplied with any matrix gives the same matrix back. So I have X is nothing but A inverse into D, right? And now X is the matrix of unknowns, or in other words, just doing this much will solve my system of system of equations here. A inverse can be further simplified as 1 by mod A adjoint A into D. So I just take the adjoint of my quotient matrix and I multiply it with the with D, right? And I divide the whole thing with the determinant of A, and that gives me the solution to my unknowns. Okay. So this is actually known as the matrix method. Right? Now here there are a few conditions. First of all, if determinant of A is not 0, obviously, so in this case you will have a unique solution. But let us consider when determinant of A is 0. Right? So these are the lesser occurring cases, but nevertheless they do occur. Now in the case that the determinant is 0 and at the same time adjoint of A into D is also 0. Right? So you see that the numerator adjoint A into D, that determinant, that is also a null matrix, and at the same time you are dividing it with 0. In this case you have infinitely many solutions. Right? But both of these conditions are known as consistent solutions. In the final one, what we have is determinant is 0, but the adjoint A into D is not 0. In this case, this is known as inconsistent system of equation, and this has no solution. Right? So this was the first way of solving equations through matrices, and this is known as the matrix method. The next one is known as the Cramer's rule. Now what Cramer's rule does is, I'll show the Cramer's rule for just 3 equations and 3 unknowns. Right? So my first, now here I have 4 different determinants here. The first one is that formed by my coefficients A1, A2, A3, B1, B2, B3, C1, C2, C3. Right? I then replace my first column here A1, A2, A3 with D1, D2, D3. Right? So I write that as X because the coefficients of X are now replaced with D1, D2, D3. Right? Similarly, I obtain delta Y and delta Z. Delta Y is obtained by replacing the coefficients of Y, right, B1, B2, B3 with D1, D2, D3, and similarly delta Z is obtained by replacing C1, C2, C3 with D1, D2 and D3. Right? So these are my 4 different determinants. Now I have a very simple solution in this case. This is given by, so my X here, the first unknown X is given by delta X by delta, Y is delta Y by delta, Z is delta Z by delta. So if there is any confusion, please note that delta is a real number, right? Discriminant is a real number. So it's just a division of 2 real numbers, not division of matrices. Right? So this is just my, so I have this simple solution here for these 3 unknowns. So X is given by delta X by delta, Y by delta Y by delta, and Z by delta Z by delta. Okay. So once this is done, again we have a few conditions for the occurrence of solutions here. First of all, well, delta is not 0, right? Because delta is occurring in the denominator in all the 3 expressions. So if delta is not 0, we have a unique solution. If delta is 0 and at least one of delta x, delta y and delta z is non-zero, we have no solution. And third case where delta is 0 and delta x, delta y and delta z, all the three are 0, right? All of them are 0. Now in that case, that actually further on further analysis we can tell if there will be infinite or no solutions, right? So that concludes this chapter on determinants. So apart from the concept of determinants, we also see the really important topics known as inverse and adjoint, and finally the way to solve a system of equations. Right? So there are two methods: the matrix method and the Cramer's rule. Obviously, both of them can be used very easily, and we will be seeing them in the question answers session, how we use them and how easily they help us in finding the solutions. So that's it for this chapter. Stay tuned for the question answers. Thank you.